Okay, so for lesson 6.1c, we're going to be working on some exponential functions with some word problems. But what we're going to do today is use formulas like the formula for half-life and the formula for compound interest to help, or a formula that maybe is embedded in the word problem, along with your graphing calculator to solve the exponential application problems. So let's start off by defining what is a half-life. Okay, and I am using my tablet here, and this is not my iPad, so bear with me because this might not be as pretty as it is with my iPad. So let's start by what is a half-life. Oh, that looks terrible. Okay, let me see if I can do a little better. It's the time it takes. There we go. For 1/2 of a radioactive sample to decay and lose its radioactivity. Okay, things you should pay attention to are the time, the time of decay. Is it in days, seconds, years? So pay attention to that. Minutes, because different elements or radioactive isotopes have different half-life units. Okay, and here's a pretty good example of a half-life when you can see that this is exponential decay, and I did not mean to erase that. I don't know. I pushed a button, so we'll back that up. Anyway, you can see here your radioactive or your exponential decay happening here. So at today, this would be in 0 years. I am 100% radioactive. You can see down here on the table or on the key what that means. And then in 5 years, only 50% of the isotope or the atoms are radioactive. And then in 10 years, it would have only 25%, etc., etc. So this is a really good example of half-life where your formula would be, well, we'll talk about formulas right now. But that's a really good example of a radioactive half-life, okay? So let's start off with this problem here. It says the half-life of carbon-14, so C14, carbon is typically, stable carbon is C12, so carbon-14 has 2 additional neutrons, which makes it unstable. Its half-life is 5,730 years. If the initial amount is A0 milligrams, that's A0, meaning that's your starting amount, milligrams, then the quantity A of T, the amount remaining after T years, is given by the equation A of T, or the formula, equals A0 times half, so your base is half. This is a half-life, raised to the T divided by K, find K. Okay, so let's talk about what that really means. So if we have carbon here, let's just draw a little graph. And T is usually being described as our x-coordinate because the more time passes, the more radioactivity will be decayed. And so your y-axis would be your A of T, okay? And let's say that, okay, so at 0 years, we would have 100% of this. We don't have an initial amount here, so we could consider it as 100% of the carbon-14. We could also consider it 1 unit if we'd like 1 full unit of carbon-14. That's up to you how you want to look at that. And your time could be in years, so at 5,730 years, we would be at 50%. Or maybe half a unit, and so that would be that variable or that value. And up here, let me put at 0 years, we have 100%. I meant to mark that. And then if we go another half-life, that would be 11,460 years. We would be down at 25% radioactive, or 1/4 of a unit is radioactive, and then the rest is not. We could also measure our x-axis here in half-lives, and this would be 0 half-lives. This would be 1 half-life is passed. This could be 2 half-lives is passed. So you kind of see that I have some double scales on my axes here, and then you have this graph, and this would be carbon-14, the radioactivity of carbon-14. So let's go ahead and just gather some points here. We have a point at 0 years. We have 100% of the radioactivity of C14, and this could be time, and then this could be percent left of radioactivity. And then at time 5730, we could be at 50%. So we could look at that data. We could also look at it as 0, we have 1 full unit at 0 years, and at 5730, we're at half a unit. I actually think I would prefer this set of data over this just because the numbers are a bit smaller, and also because I have a base 1/2 here. I think I like this idea of my A of t being 1/2. And so let's go and fill this information in. If my A of t is 1/2 and my initial amount is 1 full unit, and we're going at a half-life, and the time here is 5,730 years divided by K, what we are asked to do is to find K. What does K mean? What does K represent? So let's solve this equation. Now you'll notice here on this left side we have 1/2, and over here, well, 1 times anything is just whatever that anything is. So that's 1/2 is equal to 1/2 to the 5,730 divided by K. And notice here that we have our rule here that says if we have some base to the m equals the same base to the n, then we can say m equals n, right? So I'm going to grab a color here. This is really 1/2 to the 1 power, and so we have same base on each side. So 1 equals 5,730 divided by itself, basically, right? 5730 divided by 5730 is 1. So we can just go ahead and multiply both sides times K, and you can see that K is equal to 5,730. And so that's finding K. Now what does K represent? Well, if you think about it, K represents half-life. So let's define everything here. We have A naught. This is your initial amount. I will tell you that sometimes you're not given an initial amount, as in this case, we were not given an initial amount. So you could choose the initial amount as a percent. It's 100% of this, whatever you started with, or you could use 1 full unit or 1 full sample if you'd like. Okay, A of t is the amount remaining, the amount of radioactive isotope remaining, or atoms remaining after time has passed, or at a given time. Okay, t is the time. In this case, it was time in years. It could be time in seconds or time in minutes. And then your K, this is your half-life. All right, and so we've defined all of the parts of that formula. Okay, so now let's go do a problem. It says we have the half-life of radium is 1600 years. What is the percentage of a sample of radium? Let's take this. What percentage of a sample of radium will be remaining after 2,570 years and after 15,000 years? Okay, so let's just go back and unpack that. We have the half-life of radium is 1600 years. So that's our K, 1600 years. All right. And we are wanting the percentage of a sample remaining. So we're looking for A of t as a percentage remaining, okay, after given times. And we have 2 times here. We have time sub 1, which would be 2,750 years, and we have time sub 2, which would be 15,000 years. And so we're looking for what percentage of a sample is left. So I think that we could start with our A naught at 100% because that's how much of the sample we would begin with, our initial sample. Okay, so here's what I know if I were to just draw a little picture of this, and then I'm going to go to your graphing calculator to show you how to solve it. Okay, so this is the amount, not the amount, this is the time for the half-life of radium, and then here will be your amount over time as a percent. So we're going to start at 100%. That would be at 0 years. Okay, and so that's how much we would have at 0 years. And then at 1600 years, which would be 1 half-life, we'd be at 50%. And that would be that value there. And then at 3200 years, or 2 half-lives, we'd be down at 25%. And so that would be like that. And so we're looking at a graph that's doing something like that. Certainly not drawn to scale here, but you get the idea. So our first time value is 2,750 years. And so that would be somewhere in here, right? Somewhere in here. So what would our value be at 2,750? Okay, so let's write our equation. So I'm writing it so that I can plug it into my graphing calculator. So my initial amount is 100, and I'm working on half-life, so base 1 half, and then I'm going to do is T over K. Well, I'm going to go ahead and use X over my half-life of 1600. I'm actually just going to plug this into my graphing calculator, and then I'm going to plug in time sub 1 to get my value, my amount after 2750, and then I'm going to plug in 1500. So let me pull up my graphing calculator here, and I'm going to go to my y equals, and you can see that I already have it typed in. 100% is equal to 1 half to the x over 1600. Let's just make sure that your table settings are set so that your independent variable is on ask, because we'd like to plug in the x's that we want to look at. Now instead of looking at the graph, we want to look at the table. So we're going to grab the second function of the graph and get the table. We'll clear this out. Let me delete here. Okay, and so our first value that we're plugging in for x for our first time is 2,750. And so we're going to hit enter, and we're going to get a value. What I'd like you to do, please, is just make sure that you understand that when you get over here and you cursor over on top of your output of your y sub 1, down here at the bottom, it's giving you a more exact value. So for this one, though, we're just doing a percent. So we could just record that 38.38%. There's approximately 38.38% left at that point. So let's go back and look at our graph real quick and see if that makes sense. Well, that feels pretty good. So we're going to do our A of 2750. When we plug that in, that gave us about 30.38%. Okay, and then we're going to go back in and plug in 15,000 and have the calculator calculate that value. So go back to my X, and I'm just going to go ahead and enter 15,000. Oh, that's too many. There we go. Hit enter, and then arrow up to get a value, and arrow to the right, and look down here at the bottom of the screen. So that's about 15%. That would be a good value for that, or a good estimation for that. So about 15, not point, it's 0.15%, actually 0.15. And these are approximations, so I'm going to go ahead and use an approximation symbol. And so that's how you could use your graphing calculator, just using your time, inserting X for your time because you have different time values. There's your variable that you're plugging in, and then you use your graphing calculator to help you determine your values. Okay, so there's half-life. And now let's move on to compound interest, which is another type of exponential growth that we talk about. So here we have, if a savings fund pays interest at a rate of 60% per year, compounded semi-annually, how much money invested now will amount to $5,000 after 1 year? And then it gives us this formula here. Well, let's define what all of these parts mean. A, sometimes I would rather see this as the A of T, the amount after time, and your amount at the beginning or your initial amount versus your principal. They are the same thing, okay? 1 plus R over K instead of N, but they're the same thing again, times the KT. So you can see this formula, this equation actually come in, this formula come in two different forms. Actually, there's even more forms than that, I'm sure. But this is the amount after time has passed, okay? P is your principal. It is your initial amount, your starting amount. R is your rate. Please make sure your percentage rate, make sure that you convert to a decimal before you do your math with that. N is the number of times compounded. And this is usually an annual interest rate, so this is the number of times compounded per year. And then, of course, T is the time. And please, again, pay attention to how many times something's being compounded per year. Like, for example, if it says it's being compounded monthly, then that would be, I can spell monthly, by the way, monthly. That means that you're compounding it 12 times per year. If it was semi-annually, that'd be twice a year. So just make sure that you're paying attention to that. Quarterly would be 4 times a year. So watch out for that, because this is an annual percentage rate. It says per year. Okay, so we have a rate. Let's go back. It says unpack it 6% per year. So our rate converted to a decimal would be 0.06. So basically 6 pennies for every dollar. It says compounded semi-annually. So that would be twice a year, 2 times a year. How much money invested now? So our principal is what we're looking for. What are we starting with? Will amount to 5,000 after 1 year. So I got to squeeze our time in here. I'll get our time here. I'll just put it up here. Maybe it'll let me write it. Our time is 1 year. Okay, so here's all our information. We basically know everything but our principal. I think we'll just do this one by hand. So we get 5,000 is equal to our principal, which I don't know, times 1, which is 100%. This basically represents the whole principal, plus your 6 pennies on each dollar, divided by 2. You're compounding raised to the 2. That is not a 2. So again, 6 pennies on the dollar over 2 raised to the 2 times 1. Okay, so a couple things you could do to solve this. I would just go ahead and isolate P, since P is already factored, or it's a different factor separated from this. As an algebra student, I think I would probably just divide both sides by 0.06 over 2. I would just divide both sides by that value there and plug that straight into my calculator. Of course, you could simplify first before isolating P, but I really don't see the purpose. You know, work smarter, not harder. We're just going to simplify. So I'm going to plug this in to the calculator. So let me grab my calculator up here. And we're going to go to just our regular screen here, and I'm going to do alpha y equals enter to get a fraction, and that's 5,000 divided by parentheses here, 1 plus alpha y equals enter 0.06 over 2, close parentheses, squared, raising it to the 2 times 1, and hit enter, and you get go to the nearest penny here, $4,712.98. cents. And there you get your principal, $4,712.98. And there you go. You didn't really need your graphing part of your calculator to do that problem, but there you have it. Okay, last problem here says a house sold in 1986. That was a long time ago for $80,000. How much would this amount, what amount, $80,000, have grown to by 2015 if it had been invested at 5% per year, compounded annually, and how much in 2025? So we have some different times. So let's unpack that. Here's our initial amount. Sorry, let me call that the principal. We have $80,000. Okay, that's how much we're going to invest. How much would this amount have grown to? Okay, we have a rate of 5%, so let's convert that to a decimal. We have the number of times compounded here is annually, so that means it's compounding once a year. And then we have some times here. So we're just going to consider our time 1986 as year 0, basically, or how much time has passed. So let's do time sub 1. That would be from 2015 minus 1986. And I'm actually not going to calculate that. I'm just going to plug it in the calculator. I'm going to show you how to do that right now. In your time 2, you're going to do 2025 minus 1986. So how many years have passed? And we want to know how much is in the account. So let's write our equation. Our amount, this is what we're looking for. How much do we have if this has been invested? If we start with 80,000 times 1 plus the rate of 0.05 divided by 1, really we don't need to divide it by 1, raised to the 1 times x, because we're going to do our x-axis is going to represent our time. Okay, so this is what I'm going to plug into my calculator. Actually, what I'm going to plug in my calculator is 80,000 times 1.05, $1.05, raised to the x. That's just a little simpler version of this. So I'm just going to do y sub 1 equals that. So I'm going to go to my graphing calculator here and go to my y equals, and I have it entered here. So first I'm going to turn this equation off, so we're not looking at that equation, and I'm going to press enter and turn that equation on. And I'm going to go second graph, and I think I'll just go ahead and delete those two. All right, so we are going to enter 2015 minus 1986. And the calculator is going to calculate that as 29 years. Now, we're rounding to the nearest penny here because that's what makes sense. So again, you want to arrow up and highlight your y sub 2 and look down here, because this is just rounding it to the nearest dollar, $329,291. But I'm asking in your homework to the nearest penny. So please arrow over to that so you can see $39,290 and 87 makes the 4 or 5, 85 cents. So $329,290 and 85 cents. And then we'll arrow down to our next X. We're going to do 2025 minus 1986. But I get an 86, 1986. And that's 39 years. And again, you really need to look at that exact value because, again, it's rounded to $536,380.09. And so those would be your two values there. So we will record these. So your amount at time 29 years, which is this time here, was $390.85. And then your amount here, which is at 39 years. Whoa, okay, I pushed a button. I don't know what I did, sorry about that. Oh my goodness, I erased it. Hopefully you got that other one down. That was $536,380.09. And I'll put the 29 back up there. So 329,000. So that's a pretty good investment if you can get it, even if it's just compounding on itself once a year. That's $500,000 there, just letting that money sit there. So I suggest you all start saving when you're in your 20s and get your retirement set up. Anyway, there you go. That's how you use your calculator and formulas. Make sure that you're just making your time as your X so that you can use your graphing calculator to calculate your values for Y when you plug in different times. Have a good day.